Good. So the goal of today's lecture is to begin to get into the question of, okay, how does benzene actually react? And how do related compounds to benzene react? We already know that benzene is not an alkene, does not behave like an alkene, does not undergo addition reactions with electrophiles, but rather undergoes substitution reactions with them. So that's what we need to get into. And what I've put up here is just sort of a generalized scheme for any given electrophilic aromatic substitution involving benzene. Also, I'll just say, today we're going to focus on the 4, 5, 6 types of electrophilic aromatic substitution reactions involving only unsubstituted benzene, just C6H5. We'll worry about what if there are already substituent groups on Monday. That comes Monday. Let's first understand how just benzene behaves, and then we'll worry about the other things. So in general, I think what you'll find is that these substitution reactions have two main steps, give or take, and it depends on the details, but there should be two main steps. In the first step, it actually looks at first like it's going to be an addition reaction. In fact, the first step looks just like what an alkene does when you treat it with an electrophile. You'll have pi electrons from benzene coming out and attacking some electrophile. And like I said, we'll have 4, 5, 6 different possibilities for this, for what E plus is. And so you'll get this carbocation intermediate. The only difference is if this now were an alkene undergoing an addition, now you'd have some nucleophile attacking that carbocation. And here we really don't have anything nucleophilic. Indeed, we also don't have anything that can justifiably be called a decent base, but in all cases we'll cobble together something basically. And instead of adding to the carbocation, we'll pull off a proton and we'll undergo an elimination step. So this second step should look familiar to you. That's nothing more than the second step of an E1 reaction. So if you've forgotten about that, please go review that in chapter 11. And so we're going to find some base. There won't really be very many good choices, if any, but some base that will pull this proton off for us, return the electrons in, and regenerate the aromatic ring. The driving force for this, as you can imagine, is tremendously strong because you've regenerated an aromatic ring. True enough, this carbocation isn't terrible. It is resonance stabilized. You can also share the plus charge on any of those, or basically it's shared amongst these 3 carbon atoms. So it's not the worst carbocation in the world, but how much better to have a species that not only is neutral, but also is aromatic. So that driving force is really, really strong. And you will get some inorganic side products also, whatever this is that takes on the proton. But your major organic product should be a substitution product of this type, where you've essentially replaced a hydrogen on benzene with whatever that electrophilic group is. And that's basically the size of it. That's what all of these reactions will have in common. So I would say if you understand that, you're in good shape to understand the whole chapter. That's basically the whole thing in a nutshell. Ooh, and we're not doing substituent effects. We're starting at the beginning. Okay, so what I'm going to do today essentially is take you through these few different kinds of electrophilic aromatic substitution reactions. Again, today we're going to focus just on benzene, just on C6H6. We'll worry about substituted compounds later. Time permitting, we'll also discuss a little bit of what some of the aromatic heterocycles do, your furan, your thiophene, things like that, pyridine. And we'll have a few other types of reactions to talk about. There's actually also such a thing as nucleophilic aromatic substitution. So So basically, we've got no fewer than 4 class days set aside for this topic. And I think we'll need it. I have no issues with slowing that down. I don't want to rush through this too much. Good, so the first reaction we're going to talk about that's of this type is essentially electrophilic aromatic chlorination or bromination, or in general, halogenation. So that reaction is accomplished by taking benzene and treating it with either chlorine or bromine. But as you'll recall us saying the other day, if you just add chlorine or bromine to benzene, no reaction, which is really astonishing, because bromine and chlorine are stupidly reactive, but not reactive enough for benzene. They will react, but only if you add a catalyst, and that catalyst needs to be a metal halide species, a metal halide salt. The metal can be either iron 3 or aluminum. They're interchangeable. We do, though, want to be careful to match all of the halogens, and I'll tell you why in just a moment. But this means if we're treating benzene with bromine, we want to use either iron 3 bromide or aluminum bromide. And again, between those two choices doesn't matter at all. Flip a coin, they're interchangeable. If we're using chlorine, then we want to use either iron 3 chloride or aluminum chloride. In the end, you'll get either chlorobenzene or bromobenzene, and you will also get, as in pretty much, if not all, certainly most of these cases, you will get some small inorganic byproducts. But the major organic product will be either chlorobenzene or bromobenzene, which gets to why you want to be sure to match all the halogens, your halogen with your metal halide salt, which whether it's iron or aluminum. The reason is if you use like chlorine with aluminum bromide, I would be afraid that you would get a mixture of chlorobenzene and bromobenzene. In fact, I would be pretty confident. I've never done the reaction in real life, but as I like to say, I would bet all of you a quarter and expect to win. So there's what? There's over 100 of you, so that would get me, 25 bucks or something like that. So that's why I think you need to match the halogen to the halide in the halide salt, so as to prevent yourself from scrambling them and getting a mixture. So in terms of mechanism, by the way, you might already have noticed in these class notes, I think I'm pretty clear in terms of what you need to write in the exam to get full points. As you know, I am not fond of questions of that type. It's nothing against you guys. I care about my students. I love my students. It's just I don't like that type of question because I feel it limits you. And I want you guys to reach beyond just tell me what I need to know for the exam and what I should put to get all the points. We should reach beyond that. That's my strong belief. So that's the main reason why. But nonetheless, just to maybe avoid those questions as much as we can, or not, avoid's not the right word, obviate those questions as much as we can. I've been pretty clear, pretty explicit in the class notes about that type of thing. So let's suppose that we treat benzene with chlorine and aluminum chloride. And those are the only reagents, by the way. That's going to turn out to be important in a moment. But if we do that, if we treat benzene with chlorine and aluminum chloride, the first thing that will actually happen is the chlorine will form a complex with the aluminum chloride. The same would be true, by the way, if this were iron 3 chloride. Same exact mechanism, same exact arrows, only thing that changes is the identity of the metal. Likewise, if we switched from chlorine to bromine and used either aluminum bromide or iron 3 bromide, same exact mechanism, same exact arrows, same exact everything. The only thing that's changed is the identity of the halogen and or the metal. But the mechanism's exactly the same for all of them. But at first we need to make this very reactive metal complex of chlorine acting really as a ligand to the aluminum or iron. One of my colleagues at my former school would have been very proud of me for using the word ligand. He was an inorganic chemist, you see, and so we would always joke around about we're interested in exactly the opposite things. He thinks the metal is what's interesting and all the other stuff is just ligands, just spinach. Well, I don't think the metal's all that interesting. It's the organic portion. Anyway, it's the eternal war. So once we formed that complex, what we've essentially done is formed a chlorine molecule with a plus charge on it, if you will. And that makes sense. Remember that if the aluminum chloride or iron 3 chloride weren't here, if we just added the chlorine to the benzene, nothing would happen. They don't react. Which, by the way, I should say, if you added chlorine or bromine to an alkene, it'd react like a shot. It's exceedingly favorable. Very, very exothermic. You're boiling your solvent, and it's a big mess. But benzene is not impressed with bromine or chlorine. So we need to form this metal complex in order for it to react. And now we can form our new carbon-chlorine or carbon-bromine bond. We'll donate a pair of pi electrons from benzene. In order to form that bond, we'll also at the same time break that weak halogen-halogen bond, made especially weak by one of those halogens having a plus charge. So this is how we get rid of that plus charge on that halogen atom. And you'll get an intermediate that looks like this, kind of like what we had a moment ago. And then we need to find a base to pull off this proton and push those electrons back into the benzene ring to make a new pi bond and regenerate the aromaticity. And then we're done. Those basically are the steps. Couple things about, I felt like there were a few things I forgot to say about this. If you like, you can convince yourselves that those are the formal charges in chlorine and aluminum. You can use that formula that we learned way back at the beginning of Organic 1. And you'll convince yourself that the chlorine is a formal charge of +1, the aluminum of -1, or iron also, if it were there. So again, we have this problem of what are we going to use as the base to pull off that proton? All that's present is Cl2, AlCl3, or whatever other halogen you want, and benzene. That's it. We don't have any water. We don't have any protic solvents. We don't have anything else that can pull that proton off for us. So this is why I stressed repeatedly last term, and you're probably going to hear me say it about 1,000 more times this term. When you draw mechanisms, you need to be careful to use only species that make sense given what's in the reaction mixture. You can't just import something because it would be convenient. You can't use species that aren't there or couldn't possibly exist. And so using a water molecule, let's say, to pull off that proton would be wrong. And the way I know is by looking at what I'm given. There is no water. So we can only use a species that makes sense. This type of reaction mixture we often call a superacid because that's exactly what it is. It's super acidic. So there's nothing around that can act as a decent Bronsted-Lowry base. And really the only choice we have here is a halide ion. That's the only thing that's around. And even we don't really have so much free-floating chloride ions. They're all going to be bound to aluminum, like you see here, in the form of the tetrachloroaluminate complex, or tetrachloroferrate, if it were an iron. That's the only thing there is. And so even then, we can only make a halide ion by expelling a halide ion from the 8 complex, upon which, by the way, you'll notice we regenerate our catalyst, right? The catalyst should wind up in the end in the same form it was in the beginning. So in so doing, we regenerate our catalyst. This chloride picks off the proton. It's a terrible base, admittedly. Chloride is the conjugate base of HCl. HCl is a really strong acid. But we have no choice. There literally is nothing else. And when I think of all the times in both Organic 1 and Organic 2 that we get to use a halide ion as a base, this might be it. There might be one more later on. That's about it. You know, you can count on one hand for sure, maybe even half a hand. But in any case, the chloride ion picks off the proton, will form an HCl molecule, we regenerate our aromaticity, and we get chlorobenzene. So the mechanism would be the same with an iron salt instead of aluminum. The mechanism would be the same with bromine instead of chlorine. Same mechanism, only the identities of the atoms change. Good, so I also have a little bit of information referring you to the book on fluorination and iodination of benzene. Those are somewhat more difficult, but chlorinating and brominating benzene rings is pretty easy. Good, so that's our first reaction, electrophilic aromatic halogenation. Any questions on that mechanism? Well, all right, let's move on to our next one. Nitration means that we'll replace a hydrogen on benzene with a nitro group. And I want to be sure that everyone's clear on what a nitro group is. You can abbreviate it NO2, but I do expect you guys to know what NO2 stands for. So if you were to draw out every bond, for instance, on that intermediate, it would look like this. And yes, the question is not whether you will lose points if you don't put that. The phrasing of the question will make that clear anyways. But even if you won't lose points for writing NO2 as the abbreviated form, I expect you all to know what the structure of the nitro group is. It's of course a resonance stabilized species, right? Because I could just as easily have put a double bond here and a single bond here, and the minus charge on this oxygen rather than that one. Right, the one thing we cannot do is have two double bonds, because then nitrogen would have 10 electrons around it, and that's not allowed. So remember the principle that elements in the third row of the periodic table and below can become hypervalent. They don't have to, but they can. Like sulfur here is hypervalent. Sulfur has 12 electrons. That's allowed. That's possible. Nitrogen, carbon, oxygen, these elements here can never, ever, ever have more than 8 electrons around them. Ever. There's no exceptions. Phosphorus, yes. Sulfur, yes. Silicon, yes. But the second row elements can never, ever expand the octet. They can never have more than 8 electrons around them. So please be sure you're aware of the structure of the nitro group. Whether or not you'll lose points for not showing it is not the issue here. I just expect you to be aware of these things. Good. So in nitration, our main reactive species is called the nitronium ion, NO2+. And I'm showing the structure of that here. That's going to be our business end molecule, so to speak. And the way we make it is by mixing nitric acid and sulfuric acid in the presence of benzene. So can you imagine, talk about superacids, just imagine how nasty this reaction mixture is. You're taking practically no water present and nitric acid and sulfuric acid and mixing them together. It just doesn't get any nastier than that. Either of those two by themselves concentrated is bad enough. So you're going to mix them together. And I should say the other thing that you absolutely have to know in order to get this mechanism right, and I don't think it's asking too much, is the structures of nitric acid and sulfuric acid, which I think is reasonable for you guys to know. I expect you guys to know the structures of these small molecules like that. Citric acid might be a little much to ask, but nitric acid, sulfuric acid, it's reasonable to know the structures of these small molecules. And if you can believe it, the first step is protonating nitric acid. Whoever thought of protonating nitric acid? But that's the first step, and we use sulfuric acid in order to do that. And I don't say this happens immediately or quantitatively, but as soon as you get any species like this, this is going to lose a water molecule. That water molecule then, by the way, is essentially removed from the reaction mixture because it's now floating in this vast ocean of concentrated sulfuric and nitric acid. So it's as if it were removed from the mixture. It's a non-factor now. For us, it doesn't exist. But we do lose a water molecule, and then you get this weird NO2+. So that's what the nitronium ion looks like. That's going to be our main electrophile, and a really strong electrophile it is. So the benzene ring is again going to donate 2 pi electrons to form a new carbon-nitrogen bond. Notice that in so doing, we do need to break one of these nitrogen-oxygen bonds. Doesn't matter which, they're the same. But we do have to do that. We can't form a 5th bond to nitrogen. So, and by the way, in knowing that mechanistic step, you automatically know along with that the structure of the nitro group. That gets thrown in for free. because that's what you get after that step. You get a structure that looks like this. Now, again, we have to hunt around for something that can act as a base for us, when all we've got around is nitric acid, sulfuric acid, and benzene. I don't hear anything basic within 10 miles of that. But we have to find something, and we did here generate a bisulfate ion, which again, the conjugate acid of sulfuric acid, who would expect that to act as a base? But we have no choice. There is nothing else. Anything else would be a better base than bisulfate ion, but there literally is nothing else. So we'll use that to pull off our proton and regenerate the aromatic ring. And again, the driving force for that is so strong that as terrible a base as the bisulfate ion is, it's good enough. Would we have to worry about pKa equilibria in questions like this? I'm not sure what you mean. I can't commit to something being or not being in a question. Couldn't the generated water molecule pull that proton off? No, again, as soon as you form this, it's now lost in this ocean of strong acids. Actually, it's not even going to be a water molecule anymore. It's going to be H3O+. So we really don't have any water molecules around. It's already diluted into a vast ocean of acid and protonated on top of it. So, I mean, strange as it is, the direction of the reaction based on the pK that was really big in 227. Well, yeah, I mean, I expect you guys still to know that, not so much memorizing a bunch of pKa's, but sure, all of organic 1 is assumed in inorganic 2. So again, I've put up old exams, and I think I've been pretty clear about everything, but I can't commit to something being or not being on the exam in this or that form, or not in this or that form. But be that as it may, it's pretty dreadful when we have to use bisulfate ion as a base. But again, we have no choice. There literally is nothing else. When is the first exam again? Well, enjoy the cat content in the meantime. It's not for a while, because I think it includes all of chapter 16 and carbon NMR. Looks to me like February 19th. So by then we'll also have done the chapter on amines. That will not be on the exam. Why is the bisulfate ion not lost? Because in order to protonate that, you'll make another bisulfate ion. So you're going to have some regardless. Sulfuric acid's a strong acid. And so that's the only alkaline species we've got. And so I don't think this destroys everything you've ever learned in organic chemistry. It's not a contradiction as such. All of the other times we thought of maybe using a halide ion or a bisulfate ion as a base, there's something around that's better. Here there isn't. So it's strange, it's bizarre, but I think that's the way we need to show it. I don't think we have any other choice. We have to have something pulling off the proton. It doesn't just fall off. And even if the bisulfate ion pulls the proton off and then immediately shuttles it off to some other molecule, you know, but that I think is the best way to show it. So our product is going to be nitrobenzene. Oh, and I meant, oh no, that's different. Yep. So it does not take much, hardly any, because that proton is what's keeping this from being an aromatic ring, right? So the driving force to remove that proton is exceedingly high. High enough that even a terrible base like bisulfate is good enough. So yeah, the driving force to complete that last step is very strong. It's like I said, this carbocation isn't the worst carbocation in the world. Why does the intermediate lose the water molecule? I don't know. I've never been asked that. I know that I know that it's been experimentally determined that the reactive species is the nitronium ion, as opposed to this one. I would say that this is going to be certainly a lot more reactive than this one. The magic. No, it would be better than that, because you now have 2 pi bonds, so it's much It's much more reactive towards addition like this, whereas this maybe not so much. Is it just something to memorize then? Well, I would say only if you insist on, I'm not saying you're doing this, insist that it just is an exception and makes no sense. I think it fits right in with all of the other material. Certainly, this mechanism of forming the nitronium ion is something that you will need to know. But I think we can make sense of why, and again, I'd never been asked it, why this is so much better at reacting with benzene than this is. This is these two pi bonds with a nitrogen with a plus charge stuck in the middle of it. This is going to be much more susceptible to this type of addition reaction. This one, not so much. You even still have an atom with a minus charge on it. So again, losing the water molecule, that's going to immediately find a sulfuric acid molecule and become H3O+. Would it have something to do with being more stable without the attached water? Probably. That could very well be it. I mean, with the water attached, you've got two adjacent plus charges. That's not so good. So I think looking at these two species, it makes sense that this one's more stable. And I get it. You want to have reasons as to why things are the way they are and why you have to know them. Certainly. Totally get it. But I think all of these things that were minimizing separation of charge, certainly. I think all of these things enter into it. The driving force to protonate the water molecule, the driving force to not have this separation of charges, I think all of that enters into it. But certainly, once we get this structure, I think we can all see that's going to be a ton more reactive than this is because of these two pi bonds. And then once you get this guy, yeah, the driving force to lose the proton is so strong because you regenerate an aromatic ring that even bisulfate ion, or in the halogenation case, even halide ions are good enough for bases. So you have to put your thumb on the scale to that extent in order to have some terrible base like that act as a base in a mechanism. It has to be the case that there literally is nothing else. And I hope that I've convinced you that the water molecule is a non-factor. It's outnumbered 10 to the 20th power to 1 by acid molecules, and anyway, it's going to get protonated into H3O+ rather than H2O. So the water is going to be a non-factor. Good. No, you guys ask good questions. Is it possible to, is it possible for the nitric acid to protonate the sulfuric acid and the sulfuric acid reacts with the benzene? Good question. Answer is no. There is a way of putting the sulfur on there, but which we'll get to next, by the way. Perfect segue. But no, once you add nitric acid, you're going to nitrate it, not sulfonate it. Now let me see. Could you stop these reactions and they do they just bullet through the? I'm not sure what you mean. Could you stop the reaction here? No, that's not a stable species. It's a real species, but it's not stable. The loss of the proton is too favorable. But again, I'm not quite sure what you mean. Could you stop the reaction halfway and get a mixture of starting material and product? Sure. Like how some reactions you won't proceed with full oxidation, for example, because you need a stronger reagent. I see what you mean. And the way you know that this is not that type of reaction is because there's not multiple structures possible. There's only one nitro group here. There's no other thing that you can put on there from these molecules. So that's how you know that these are different. You're thinking of like the difference between PCC and chromic acid, for instance. That's an oxidation reaction. This is a substitution reaction. So now you might also be talking about some of the substituent effects, which we'll get to on Monday, but I'll always at least try my best to show what you have to know and how you can know whether you will or will not proceed. So I'll try my best, but that's not going to be the case today. We'll either get the product or we won't. Is that kind of what you mean? I just want to make sure I'm answering your question. Good. Well, someone asked about sulfonating benzene. That's a thing too. The mechanism on page 485, as I say here, is not wrong. That one's acceptable. I'm going to show you another one, which I think is equally good. In fact, I think both of these actually happen. But essentially, what we're going to replace our aromatic hydrogen with is a sulfonic acid group. Those are two acceptable ways to abbreviate the sulfonic acid group. I'll show you also what that looks like drawn out. Again, the question of what you will or will not lose points for drawing or not drawing is not the issue here. I certainly expect you guys to know the structure of the sulfonic acid group. And instead of nitric acid and sulfuric acid, our reagent is called fuming sulfuric acid. It's sulfuric acid with sulfur trioxide added. And this is nasty beyond compare. Sulfur trioxide is actually the acid anhydride of sulfuric acid. So as bad as concentrated sulfuric acid is, you've probably been warned about how badly that will burn you. So to concentrated sulfuric acid, we're adding its acid anhydride. So that's why they call it fuming sulfuric acid, because it's literally fuming. Smoke is coming off it. Yeah, no, you can't taste it. You can't take a bath in that one. But as for the acid anhydride, if you take away H2O from H2SO4, I think you'll see you get SO3. Why do the conditions have to be so harsh? Is because aromatics are so stable and unreactive. Exactly right. Couldn't have said it any better myself. And so this shows you how stable benzene is. We didn't have to go anywhere near this extent to react with alkenes. But benzene, you've got to really kick it in order for it to react with any of these otherwise very strong electrophiles. So yes, I like the way you put it. You all can use this as, I don't know, evidence or further supporting information as to just how stable benzene is. This is the extent you've got to go to get it to react. So, but the book's mechanism is right. Here's another one that I think is also right. And I would bet you anything both actually happen. So I don't care whether you use this mechanism or the one in the book. I think they're equally acceptable. So another way to show the same thing, here is your SO3, by the way. That's usually the best way to draw it, I think. Again, we're going to get 2 pi electrons from the benzene ring. Oh, another thing, notice, by the way, when the name of this reaction, sulfonation. It's in the class notes, sulfonation. So, but it doesn't have a person's name attached to it like the Friedel-Crafts reactions do. In any case, what I was saying was, notice that even if you're the type to draw benzene with a circle, which actually, if we were in a classroom and I were drawing on a chalkboard, I usually draw benzene rings that way, which it's fine if you do and it's fine if you don't. On ChemDraw, it turns out to be much easier for me to just use the Kekulé structure. Putting the circle in is kind of tricky. But in any case, regardless of that, when you're drawing a mechanism, we really have no choice. We have to kind of pretend those 3 pi bonds are localized. They aren't. We kind of have to pretend that way. Now, it doesn't matter which of the resonance forms we use. What's the difference between nitration and sulfonation? Well, with sulfonation, the reagents are SO3 and H2SO4. With nitration, the reagents are nitric acid, HNO3 and H2SO4. So that's how you can know what you're looking at. The reagents are different. They both include sulfuric acid, so sulfur trioxide, that we really already have our electrophile. Sulfur trioxide is a very strong electrophile in and of itself. So our benzene ring donates pi electrons and forms a new carbon-sulfur bond. And then we're in the same position. We need the cyclooctatetraene behave like benzene or like a cycloalkene. A good question, the second thing. Cyclooctatetraene is not aromatic. Didn't we make a model of that the other day? So it's not planar either, it's tub-shaped. So yeah, it's a very reactive alkene and would behave like any of the other alkenes. No, it's perfectly fine. Yeah, cyclooctatetraene is not aromatic. That will undergo addition reactions like any other alkene. So right now, where was I? Oh, we're in the same position as before. We have to pull off this proton in order to regain the aromaticity. And of somewhat less importance, we also need to protonate this oxygen to give our neutral final product molecule, which is really not a problem since there's a ton of sulfuric acid around. So that second one is a solved problem. If you were to ask me which occurred first, I would tend to lose this proton first, because I feel like it's more of a priority to regenerate the aromaticity than it is to protonate the sulfonate group and give the free sulfonic acid. But again, there's really nothing else around but bisulfate ions. Whenever you have sulfuric acid, you're going to have bisulfate ions also. It's a strong acid. But that's really the only thing available to us to pull that proton off. So we do that, we regenerate the aromaticity, and then we can use a sulfuric acid molecule to put a proton on the sulfonate group and give you your free sulfonic acid. I was going to say something though. Drat. It was something about the protons. Oh, I remembered. Students will often ask here, well, can't I save myself a step and just use this oxygen to pull off that proton and go straight to the product? I'll save myself a step then. I won't have to write as much in the exam. Nice try, answer is no. And the reason that that doesn't work is this would be a four-membered transition state. If you count from the oxygen to the hydrogen, it would have to get into the position of a four-membered ring, and it can't reach. It's too strained. So the proton's too far away, if you will, from the oxygen. It can't get close enough to pull it off. Four-membered transition states are extremely rare. There are a couple, but they're really, really rare. Now, if this were one atom further out, or two atoms further out, and you had a 5 or 6 membered transition state, then we'd be good to do the intramolecular proton transfer. But with a 4-membered transition state, no way. It can't reach. So yeah, I'm glad that actually occurred to me. Good, that's basically it. Now we've got our benzene sulfonyl chloride. All right, well, I've already put this on eCampus, by the way. So it's already available for you. Good, and answer trick question. Turns out they're all aromatic. These two species both have 6 pi electrons. This one we might have done in class, actually. That's the cycloheptatrionyl cation. So you've got 6 pi electrons, you've got 7 unhybridized p orbitals. And the way I've drawn it here, they're perpendicular to the screen, but 6 of the 7 p orbitals have 1 pi electron in there, and of course the last one is empty, which is allowed. This guy here is an interesting one. What I think you will find is that the lone pair on nitrogen is in a hybrid orbital. So that's sticking out from the ring. And on the oxygen, sort of like in furan, I think you'll find one of these lone pairs is in the unhybridized p orbital, and one of them is in the hybrid orbital, like for the nitrogen. So in the end, you have 6 pi electrons, 4 in the 2 pi bonds, and 1 of the 2 lone pairs in oxygen. This guy over here is brutal, but again, some of you will get that on OWL. And what I think you'll find is all 8 carbon atoms have a CH bond. That CH bond, that bonding pair is in a hybrid orbital, one of the sp2 hybrid orbitals. And of course, 6 of the 8 unhybridized p orbitals on these 6 carbon atoms. Again, those are perpendicular to the screen. Those 6 will each contain 1 pi electron from the pi bonds. And then we still have unhybridized p orbitals on those 2 carbons. And they will each contain 2 electrons. In each case, it will be the 2 electrons in a lone pair. And you have 2, 3, 4, 5, 6, 7, 8, 10. So you have a total of 10 electrons. Bizarre. You can call that the cyclooctatrienal dianion, if you like. And it is a thing, has been well studied. And in spite of having a charge of -2, it is extra stability that you wouldn't normally expect due to being aromatic. So that's been studied out the wazoo. But that, like I said, that's already on eCampus for you guys to look at. Good. Lone pairs don't necessarily count towards bonds for sp2 and sp3 counts. Well, yeah, I think that's right. I'd have to go back to it. We assume nitrogen or oxygen is sp2. Right, you assume every atom in the ring is sp2. We're going to assume the molecule's aromatic, and we'll try to account for all of the electrons and see if we break any rules. And in all of those cases, we turn out fine. We don't break any rules. So, yeah, that's already on eCampus if you want to take a look at it. Good. So I think that's all we need for this. Good. So that just leaves these two so-called Friedel-Crafts reactions. And they are important because by them we make new carbon-carbon bonds. And as I think I've brought up before, anytime we make a new carbon-carbon bond, that is money in the bank. That is, I can't hear you over the sound of all my money type of thing. Because that's how we make drug molecules. It's important to be able to go from simpler molecules to more complex ones, and anything that can form a new carbon-carbon bond is potentially valuable. So in the case of the Friedel-Crafts alkylation reaction, I think we all know what an alkyl group is. What we're going to do is replace one of the ring hydrogens with an alkyl group. And the way we do that is we'll treat benzene with some alkyl halide, and again, some metal halide salt, either aluminum or iron 3, either chloride or bromide. As for the halogens here, I still think it's best practice to match all the halogens. Since we're not forming any new carbon-halogen bonds, I don't know how easy it would be to get a mixture. I would still be afraid. If it were me doing this in real life, I would try to make sure I matched all the halogens. So if I used an alkyl chloride, I would use either aluminum chloride or iron 3 chloride. If I used an alkyl bromide, I would use either aluminum bromide or iron 3 bromide. So I just think that's best practice. You will get a molecule of a hydrogen halide as an inorganic byproduct, but the major organic product should be what you get by replacing one of the hydrogens with an alkyl group, probably, because there's asterisks here since we're dealing with alkyl groups and carbocations. So I'll show you what I mean here. We also can do acylation. So here I've defined an acyl group for you. Any type of group, any group of this type is called an acyl group. Some of them have names. I guess R is CH3. You know that one. That one's an acetyl group. So that's one type of acyl group. Or if R is a benzene ring, you've got a benzoyl group. So some of these have names, but in general, they're called acyl groups. And so we do acylation in the same way that we do alkylation, except instead of an alkyl halide, we'll use an acid chloride. So that's a functional group that we've seen before. And so in addition to the acid chloride, of course, we need our Lewis acid catalyst. That should then be either aluminum chloride or iron 3 chloride. Doesn't matter which. Either of those two metals is fine. In the end, you will get a ketone of this type. And you would also, of course, get a molecule of HCl out at the end as an inorganic side product. But your major organic product, which is what we really care about, is going to be an aromatic ketone, looking something like this. So in both cases, you get a carbocation. And again, I was really clear in the notes about what you need to put. But the way it happens from an alkyl halide, regardless of what R is pretty similar to what we saw with forming let's say, the reactive species with halogenation. At first, we form one of these funny 8 complexes, as we call them, like the ATE, like 8 food, as in ferrate or aluminate. But we form one of these metal complexes of this type, and then the carbon-halogen bond breaks and you get a carbocation. At which point, by the way, I'm hoping that red flags just went up in everyone's head. Because we've generated a carbocation. That means what it always means. Whenever you have a carbocation intermediate anywhere in any reaction mechanism, gotta look out for carbocation rearrangements. That's the big weakness of Friedel-Crafts alkylation, is unless you want that rearrangement to occur, you have to be careful to pick an alkyl halide that forms a carbocation that's not going to rearrange. The acylation reaction does not have that problem, as we'll see. So, and in fact, we have ways, they're in your book, we have ways of reducing ketones of this type reducing the carbon from C double bond O to CH2. So there's a few different ways to do that. So that's one way of getting around a potential rearrangement problem. You can do an acylation and then reduce the ketone to CH2. So like I said, that's there for your perusal in the book. Fine. So what does this look like then for acylation? Very similar. We have our chlorine atom attacking either aluminum chloride or iron 3 chloride, and whichever of those two is the one you're given is what you would draw here, if you were showing that. And then we once again break the carbon halogen bond, and you get an interesting species known as an acylium ion. That's a resonance stabilized species. You can also draw it with a double bond, and the oxygen's neutral, and there's now a plus charge in carbon. So the plus charge is shared between carbon and oxygen. And you can draw it either way. Both are perfectly acceptable. And since that's the case, we have choices in terms of how we draw the mechanism. Let's do a sample Friedel-Crafts alkylation, one that would actually work for us. Let's say we treated benzene with isopropyl bromide in the presence of iron 3 bromide. This answer would receive full credit. You're going to form the isopropyl cation. That's now not going to rearrange. It's only secondary, but there's no way to get a tertiary carbocation. And if it rearranged, you'd only get a primary carbocation, which is worse. So that's going to be configurationally stable for us. Benzene will attack that carbocation. We get, again, this type of intermediate. It's a resonance stabilized carbocation. And then there's nothing else that can act as a base for us. There is no water. There is no protic solvent. Nothing like that's there. We can tell by what we're given. All we have is benzene and isopropyl bromide and iron 3 bromide. I don't see anything there that's strongly basic at all. That's a superacid solution, exceedingly acidic. So we have no choice but to expel a bromide from this ferrate complex. We use that to pick off the proton and regenerate the aromaticity. And you would get isopropyl benzene, which I guess is also called cumene, C-U-M-E-N-E. That's a compound with a trivial name. So I point out about carbocation rearrangements here. Acylations, as we said, Friedel-Crafts acylations don't have this problem. So let's say instead we treated benzene with propionyl chloride and aluminum chloride. I would expect we would get this aromatic ketone. And here there would not be any rearrangement. That would be the exclusive product. So I've shown here two different ways to show the mechanism. They are equally correct as far as I'm concerned. They only differ in which of names like, yeah, you're going to need to know names like toluene. There's a table in the book, and of toluene's one, cumene's another, benzoic acid, benzaldehyde. You know, these things just are so common. We use those names all the time. Aniline is aminobenzene. Yes, I do expect you guys to know those names. Even though you can look it up, you're going to waste a lot of time if you need to look it up each time. So yes, there's a table in the book that I'll recommend you look into. There's not that many of them, maybe 8 or 10. I bet at least half of them you know already. But they show up so commonly that you'll handicap yourself if you don't know those names. Good. So similar reaction mechanism to the others we've seen so far. You've got your benzene attacking your acylium ion. And again, we have no choice but to use the tetrahalo illuminator ferrate complex to kick out a chloride ion to pull off that proton, and you get your product. Or again, you could also draw it like this. Oh, I guess I forgot one lone pair in oxygen, but you see what I mean. That lone pair, of course, is still there. But really the same thing. It's just an alternate way of drawing the same thing. And the great thing is, let's say that we did not want to make this, but in the end, we really wanted to make propylbenzene. We could now easily get that. We would just reduce the carbonyl to a CH2. And you can do that with catalytic hydrogenation. You can do that with, what's that guy's name? So-and-so reduction. Anyway, but those reagents are there for you to learn about in the book. There's no mechanism really for them. But that would reduce the carbonyl to a CH2, and you'd get propylbenzene, which you could not do with an alkylation. If you treated benzene with not isopropyl bromide, but propyl bromide, 1-bromopropane, you would still get isopropyl benzene as your product because it would rearrange. You'd get a 1,2 hydride shift. So that's basically it for the reactions themselves. Next, and I give you some further advice here. Next time we're going to address the issue, what if we don't have just benzene? What if there's already a group attached to the benzene ring? That's Monday. We'll get there next. So other than that, that's about it. I'm out of time, so have a good weekend. We'll see you Monday.